Let's go. Okay. So whilst I try to get network access, I'm going to explain what's Gentoo Hardened. I mean, I have done it so many times that I don't even need to look at anybody to be able to do it. Gentoo is a Linux distribution that is source-based. That means that you basically download the sources using a tool, and that tool will compile everything for you. I mean, it's not like Linux from scratch, where you have to actually do the compilation by hand, but it's quite close in the sense that it will actually, you usually don't use binary packages with it. You can use binary packages if you want. You can make your own binary packages for your own machines, but you usually will not find public binary packages, at least not official ones. So one of the things that this gives us is that we can actually enable a lot of hardening features on the compiler level when we are compiling to sources. For example, things like ASLR are really effective if your binaries are compiled using position-independent code. So the binary will be at a random position every time that it's executed, so an attacker cannot try to figure out where the little bits of memory that he wants to use, or the little snippets for the return-based programming are found. In a similar way, for example, we can also use things like a stack smashing protector. That's hopefully old. I mean, I think a stack smashing protector was like a fad 5 years before I started using Gentoo. And I am a bit old, I guess. So, and despite that, it has only started being used by distributions in the last 5 years, maybe 4. And usually it's not even applied everywhere. It's only applied using some heuristic in order to make the code as strong as possible without having side problems. So, give me a sec, please. Harden it. Okay, let's see if I have. I will go for version 2. Okay, so now that you understand more or less what's Gentoo Hardened and what is the idea behind it, I should explain you why this is not part of Gentoo itself. I mean, you could say, okay, security is nice. Why don't we provide that to everybody? Why do we actually require that you follow a few complicated steps in order to be able to use it? And the reason is that, well, Gentoo is for risers. Jokes aside, most of the users that use Gentoo just want to get like the last teeny bit of performance that they can out of their computers. So the security measures are kind of in the way for it. As a matter of fact, Gentoo hasn't provided SSP until I think it was GCC 5.2 or 6.0 by default. So what that means is that most users have been running a really insecure system, even more insecure than Ubuntu, Debian, or whatever else you can think. But it was their choice. I mean, they could actually use the hardened profile if they wanted to care more about security than speed. So that is the main reason why it's not part of the full Gentoo project. I mean, usually the user space hardening features work quite well everywhere because they are really well tested. They are really easy to test. But when it comes with things like integration with the old GRSec patches and stuff like PAX protection, that kind of stuff doesn't work so well, so you actually need to have a little bit of knowledge to know how to troubleshoot the problems by yourself. So, well, let's speak about the protection systems that are offered. I'm going to focus first on user space protections. Then, depending on how much time we have, I will focus on kernel space protections. It's very important that if you have any questions, if you cannot understand what I am saying or you don't make sense of it, raise your hand and tell me that I am having this problem so I can try to explain things in a way you can understand, okay? My objective here is not that you guys decide, oh, I'm going to install Gentoo Hardened everywhere. It's that you understand how the protections work so you can use them even if you want on your own distros or whatever it is that you guys are doing. I mean, aside from Hanno over there, is any of you a developer for any distro? Debian, Ubuntu? Okay, so it's only 2, 3, counting me. Well, Alex, raise your hand. You are kind of a developer, or you said 2. I know you are not anymore, but Okay, so let's talk first about the protections that are offered at compilation time. So as you probably know, usually there is two stages when you are generating a binary. First, you have to compile the source code into binary code, and then you have to pick out the small bits of binary code and put them all together. The first thing is called compilation. The second step is called linking. So at compilation time, one of the features that we have is, as I said, stack smashing protection, SSP. The idea behind the stack smashing protection is that you will place some value in your stack. So, you know, actually I think, is it too late to say, can we use the screen? Because I do have a really good example for this. Nope, it's an HDMI, it's all I need. I don't mind if you don't record the slides because they are publicly available. It's more so they can see on the screen what I am trying to explain. Okay. Yeah, it might be on the stream, but my laptop basically died when I connected it. Nope, that was actually my fault. Okay, let's see if this works. Nope. Okay. Yeah, this is so secure that. Yes. Okay. Nah, it doesn't matter. So I can explain this by hand. So basically, Alex, come here. So now, no, come here, don't be afraid. Is it okay if they record you?
Yes.
You know, you have to ask first. So Alex here is going to be on a stack. So as you can see, we are going to do our own procedure call. So the first thing that we are going to put here on the Alex cap is going to be the return direction, so we can continue working on the previous procedure afterwards. And here we are going to put our arguments, so the function knows what to do with them. And afterwards, we can put, for example, the variables, local variables that the function is using. The order is a little bit different. I mean, you actually put first arguments, then this will be our return direction, and this will be our different parameters and other kind of variables that we are using on our function. So what we do with SSP is that we introduce here a value that will check whenever we return. So the idea is the following. If we want to return, we check this value. If the value doesn't matches with the one that we put in here, then we will kill the program because we know that something has gone awfully wrong and something has actually tried to overwrite the return address that we are going to use here on, well, Alex cap in order to return back to our normal function. Does that make sense to you? Could you guys visualize it? Thanks a lot. So that's basically SSP. So as you can figure out, you only want to use SSP when you have functions that are working with memory directly, as in using pointers and that kind of stuff. When you use safe programming, like type-based programming, you don't have a need for that. And that's more or less what heuristics in the compiler try to predict. The compiler tries to figure out which functions are safe or unsafe, and which functions are at risk to actually cause an overflow. In Gentoo Hardened, until GCC 4.8, we used to put this value on every single function. Now GCC is a little bit better, so it can actually detect safe functions, that is, functions that are not doing anything with pointers or memory. So these ones get excluded because we use the strong stack protector, but we don't use the usual stack protector that use the heuristics. Most distros, on the other hand, will use the heuristic-based stack protector that is quite okay, but it still has some small risk that a function that is not handled by it is actually vulnerable. So, well, that is about buffer overflows. That's about SSP. And so you can understand what we try to prevent with SSP is the ability of the attacker to actually overwrite any data on the arguments and the return value that we are going to use to know where to continue execution on the previous function. Perfect. So now let's speak about PI, peak, and all this kind of stuff. PI stands for Position Independent Executable, and peak stands for Position Independent Code. If you want to make a position independent executable, you have to have position independent code that you use at link time. This sounds quite trivial, but it's actually a bit hard to do on some architectures. I mean, x86 is a real pain in the ass because you have to keep a specific register out of the few that you have on the processor, so you are able to go back and find in which place the other functions that you need to call are found. On AMD 64, that register is actually allocated by default. It's part of the ABI. So you will find that you might find 32-bit code that won't work well when you use position-independent code, but it will work flawlessly on 64 bits. And that is because the ABI is different. The 64-bit ABI actually intends that all code has to be relocatable. And what do we use that for? Well, if your executable is independent, it can be placed anywhere, and your libraries can be placed anywhere, you can have the kernel, whenever you try to call one of the executables, to place the executable part of the program randomly on the memory, so the attacker cannot figure out which is the exact address on which the different gadgets that it wants to use to do return-based programming are found. In a similar way, another of the features that we have is called fortify source, and this is basically a glibc-based protection. Fortify sources, or fortify source, will try to check for some simple cases of stack overflows and some other kind of memory corruption vulnerabilities, and it will do so at a more or less static time with a little bit of dynamic overhead. And that basically helps to protect against some functions like memset or memcpi, but not in all cases. You actually need to have a very well-delimited, you need to pass as a parameter a delimited vector, so you actually explain to glibc, which is the exact size that the vector is supposed to have in order to prevent the overflows. Another final feature that I want to comment, I mean, raise your hands if you have heard about the stack class. This stack overflow thingy that happened a few years ago, or years. It felt like years because I had to spend a whole week doing research in order to write an article about how it worked, but it was actually 2 or 3 months ago. Well, in the compiler, you have a feature called stack check. I mean, you probably, if you have read that story, they were like, yeah, if you use a stack check, you are secure. That's technically not totally true. Stack check is intended to leave 2 pages of security somewhere in the middle, so that you can actually run a signal handler in case that you have a stack overflow, and you can handle that gracefully. But in the hardened systems, that actually did work, because unlike the original kernel, we left 64 pages, if I recall correctly, or 16 pages by default. So the 2-page gap that it was used by stack check would actually work as intended, and it will actually be able to detect if a stack overflow was happening. And I can proudly say that, well, Gentoo Hardened actually was secure against the stack class, because we had been using a stack check for like 2 or 3 years since now, when we introduced the GCC 4.8 as main GCC compiler. If you are a distro developer, I strongly recommend that you enable a stack check, because, I mean, these kind of vulnerabilities can only be fixed in that way. You cannot fix a stack overflow if you don't check that you are not overflowing the stack, given the way in which the stack is expanded. The only way in which you could be doing that in a more efficient way could be if you could tell the kernel, I want to expand the stack up to this size. So I need to add maybe 20 bits or 100 bits or whatever. and the kernel failed if you don't do that correctly. But that will require a lot of performance in order for it to work correctly, because then you would need to call that function whenever you do a function call, and that's awful. I mean, even a simple hello world usually makes around 20 or 30 function calls just to show you hello world. So, okay, now we also have some link time protections. We basically mark all our binaries so that relocations are placed on read-only memory. So basically, the binary will try to find where to find the functions from libraries and everything at some point. And we set that direction in read-only memory. So once this has been activated, or you have started executing your binary, you will be completely unable to modify that direction unless, of course, you manage to change the protection levels of the memory. I mean, or your architecture doesn't support read-only memory. That can also happen, I guess. But in most cases, you will actually be unable to, for example, inject a new function on the binary and tell it, okay, I want that the printf function that you are using is actually my own function, and then you have to return back to the libc function. We also use another feature of the linker called bind now, or early binding. And the whole idea is that in most cases you use lazy binding. The idea is that you only will link a library when you need it. In Gentoo Hardened, we configure the linker so that all the libraries get linked as soon as you execute the binary. This makes the program work a lot slower, because you will find that there is actually a lot of binaries, especially on desktop systems, that link against everything they can, even if they are not going to use it. They are going to link with ALSA, even if they are not planning to use Zone. They are going to link against every single existing X library. And you guys better don't get me started on Mozilla Firefox, okay? So, yeah, if you have to do this linking process every time that you start a binary, it's a lot slower. On the bright side, if you actually want to do some real-time based programming, this is also really efficient, because that way you know that your binaries will not start linking libraries halfway during the execution and therefore ruin your expectations of real time. That basically covers everything that is on user space. Is there any questions? No? Have you been able to follow my talk so far? I mean, I know that my Spanish accent is really thick. I can make it even worse, but I'm trying not to. Okay, so let's talk a little bit about kernel level security, okay? Most of what I am going to tell you applies to GRSec. As you know, GRSec is no longer open source. Well, I hope that if Spender is seeing this, he is not going to kill me, okay? Spender is not open source in the sense that now the sources are not open to everybody, not in the sense that they are not following the GPL version 2. Okay, Spender, please don't kill me if you see this. So the whole thing is that since they have decided to convert GRSec patches into a commercial patch, so you have to pay in order to get access to them, unless you get some really nice person that has already access to them and says, well, it's GPL version 2, so I'm going to exercise my right of giving you access to the patches, so here is a copy. Most of these things are going to be a little bit useless for now. I mean, the current kernels might not support most of the features here, and the main problem is that most kernels actually have a watered down version of these features, because there is like a lot of conflicts, and of course, for me, security is the most important, but maybe for the guy that is developing the 10 gigabit Ethernet network card driver from Intel, really cares a lot more about stability than security, because if the server goes down, well, we are fucked up. So that is why you will find that most of the features that KSSP is introducing into the kernel are not as strong as they are on GRSec, but it might be one of the 3 options that you have in order to use a hardened system. I will go back later on the talk about how to install a hardened system and what you can do if you are using Gentoo Hardened and you don't have well, access to the GRSec patches. By the way, I don't have access to the GRSec patches. I want to make a note here, and I think none of the Gentoo Hardened developers have. Just so you know. And this staying here. Okay, so let's talk first about address space layout randomization. I have told you shortly about it when I was speaking about position-independent code. Address space layout randomization basically means that you will place every single bit of the program in a totally different address every time you run it. So for that, you need to have a program that is able to run no matter on which place you are placing every part of it. That is why position-independent code helps strengthen a lot address space layout randomization. Following with this, GRSec had some really nice features. I mean, GRSec, actually I think that was PAX that did it, had a feature called RandMap. A RandMap basically tries to do the same whenever you try to do a call to map some file into memory. So it will place it whenever it wants, unless you use the position fixed flag, which means that you are telling the kernel, I want it to be at exactly this address. In a similar way, they have another feature called randkstack. That basically means that the stack of the kernel will be placed randomly whenever you do a system call. So it will not be on the same place every time you do the system calls. And that makes it, that makes it a lot harder to try to exploit an overflow on the stack in order to try to get code execution on ring 0 or kernel level code. Another feature that they have is called UDREF. I think UDREF nowadays is mostly done by a plugin. In the past, it was done by hand, which was a pain in the ass. I mean, you know how many functions exist on the kernel that try to send code to user space? It's an awful amount of them. I mean, you are probably going to have nightmares and dream with kernel code every single night for the next coming 5 months. If you have to go one by one and try to find where they are placed and have to replace everything. So you actually make the function say, okay, I only want to copy these 2 bits or 2 bytes of memory to user space and not more. And I want you to verify that that's actually the case. And now think that then the next version of the kernel comes out and you have to invest another 2 or 3 months updating your patches so everything gets up to date. That's why they moved everything into a GCC plugin. Another feature that has been there for some time is called map address. Basically, it makes that you cannot map memory regions on the first sectors. So, for example, you cannot try to say, you cannot make a program map code on the null pointer because have you guys programmed it in C? Raise your hands. C, C++? Hey, I really like this audience. Nice. This is going to be easy. So, as you probably know, the null pointer is exactly 0. Well, not exactly because it has a different type. But if you cast it to an integer, it's 0. It's basically at the bottom of the memory. And you can actually map memory on position 0. So you can use an mmap call and tell the kernel, yeah, I want to map this file on position 0. So whenever you access null, instead of getting a segmentation fault, you will actually get whatever you place it on address 0. In GRSec, that is prevented using a specific feature for it. I think on recent kernels that is also prevented nowadays. But you can disable that feature using the proc file system if you want to use a specific code or using a specific capabilities on the process. Then, of course, we also have non-executable memory. I mean, basically, I have to give credit to the PAX team here because they were the first group that introduced the idea of non-executable memory. Then Microsoft followed it, and they basically made non-executable memory happen before it actually was a reality on the Linux kernel. So a round of applause for the Microsoft developers. They were better than Linux for once. And the thing is that what the idea is that if you know that you have some memory that it's only going to contain code that has not to be written by anybody, you can make that, you can mark that section as, no, sorry, that's a different feature. never mind. Non-executable memory. You have basically this part of memory that you know is never going to contain code, and you don't want the processor to run anything on it. In that case, you can mark the specific pages using the NX flag on AMD 64, on 32-bit architectures. You can use PI extensions if you have them in order to mark non-executable memory. Otherwise, you have to use segmentation-based approach. And by doing that, whenever the processor tries to execute code in that memory region, it will produce a segmentation fault because it will not be able to access the memory for execution, and hopefully that will kill your process and you will prevent a, well, privilege escalation or remote code execution attack. We also have mprotect restrictions. I think that is never going to make it into the mainstream kernel, sadly. The idea behind mprotect restrictions is that you actually enforce non-executable memory everywhere, except in binaries that you mark as don't enforce this, because they have to use just-in-time compilation, like, for example, some Java binaries. I think up until recent versions, Python did also that because it was using the foreign interface library, libffi, and libffi used trampolines, and they used trampolines in a really weird way, so it couldn't be emulated. And, well, Firefox, basically everything that uses OpenGL nowadays, all that needs to be marked, so you actually tell the kernel that they are allowed to have memory that is executable and writable at the same point of time. Chromium, yeah. Well, Chromium is included actually on the GL library users, so you are fucked even if you actually disable the Firefox. Actually, because of the JavaScript engine, has a similar problem. But I think that could be disabled at configuration time. So when you are compiling Firefox, you can tell Firefox, no, I don't want to have a just-in-time compiler. I want to have everything interpreted. I'm not sure if Chromium has that possibility nowadays or not, but it does? Fucking Google. Okay. Then another feature that we might or might not see into the kernel was reference counter overflow protection. That is implemented using a plugin that will use a specific type in order to mark what is considered a reference counter. So basically, it will modify the code, so whenever you want to increase the reference counter value, it will check if you are already on the max. If it's the max value, it will prevent you from doing anything else to that specific reference counter. So that basically means that you convert what could be a double free or a use after free attack into a what's it called, memory leak. So that will mean that if somebody starts exploiting such an issue in your server, you will have to reboot the server eventually because you are going to run out of memory. But at least it will be eventually and not when the attacker actually takes full control of it. So it's a little bit better. Another feature that we have that I hope that we see on the Linux kernel soon is sanitization of free memory and the kernel stack. So the idea is that whenever you free a page from memory, that page will be cleared out. So you can be sure that if you are freeing memory, that memory will not be kept on your computer for a really long amount of time. Because otherwise, if somebody comes afterwards and does a dump of memory, and say, for example, you have been writing your password on some random web page, he might be able to find your password in clear text in memory because that memory page hasn't been reused and therefore has not been cleared before allocating it to another process. Same with the kernel stack. We have kernel stack sanitization, and that means that basically before you return from any system call on kernel space, you are going to clear the whole stack or the part of the stack that was used, in order to prevent that if you make another system call, there is non-initialized memory that contains information that could be interesting and that could be extracted by an attacker. Well, then we also have writes being denied on the memory, kernel memory, and port devices. this is kind of a mini mandatory access control thing. I am reasonably sure that it can be implemented using, for example, Linux. And now is when Spender will come back and say, no, it cannot be implemented on Linux because Linux can be disabled once you have enabled it. That's actually true, but meh, whatever. At least it's better than nothing. They also have some features that intended to attack known vulnerabilities or known really risky areas of the kernel, like disabling the old PM86 mode. I think that can be done on the configuration of the kernel nowadays. They also disabled privileged input-output. That is a really good way to mess up with your XOR if you are not using kernel space drivers for your graphic card. So if you need to use user space drivers, make sure that you actually don't disable privileged input-output. Then they also had some features that intended to prevent disclosure of information that could be used by an attacker, even if you use address space layout randomization. For example, I think I know which is the best way to explain this. Who of you is using the SSH agent or the GPG agent? I am. Yes, okay, so you know that the SSH agent or the GPG agent keep a copy of the keys that you are using decrypted on memory so they can use them whenever you try to access a host or you try to sign a message. They usually protect that memory in order to make it hard for an attacker to get access to it using, for example, a debugger. But now think that, say, for example, the SSH agent had a buffer overflow vulnerability. And an attacker wants to find information about the address layout of your specific instance of the GPG agent in order to extract your private keys and start sending messages on your behalf. So basically, they made it impossible to get that information from the kernel unless you were the parent of the process that you were trying to attack. They did that, for example, preventing access to /proc/PID maps that gave you the whole listing of the mappings that a specific process had made. Same with the smaps file, that is a slightly different version of it. And they also modified some system calls so they could never return information of that kind for another process. And of course, they had a feature called Hardened Ptrace that made it hard for a non-parent process to run the ptrace command that is using for debugging, so they could not actually try to make picks and pokes of memory to figure out which was your key. So that basically covers most of the kernel features. I mean, I could stay speaking for this like for 20 or 30 more minutes. A few more interesting features was, for example, that GRSEC will stop brute forcing. I mean, if it detects that you are trying to do a privilege escalation because you have basically provoked some kind of buffer overflow attack on a root program, it will prevent that program for forking in the parent program for forking in some time. So you cannot actually try to brute force the addresses that it's using, because whenever you run a fork, you will get an exact copy of the process. So if you kill the kid process, but the parent process is still running, whenever it does another fork, you will be able to actually figure out which is the addresses that the process is using after doing a shitload of attempts, but knowing that eventually you are going to succeed at that. I could go for really, really long time, so let's try to make this a little bit faster. They had a shitload of features in order to prevent disclosure of information that could be useful to attackers. If you want to see the code around that, well, you can check how they hide kernel symbols, kernel processes, how they apply specific restrictions to the proc file system, so that only the user that owned a process could access the specific process information. They also applied a lot of restrictions on the system and debug FS file systems. They have restrictions that prevent linking. That was in order to prevent some Apache vulnerabilities that are not happening so much anymore. They, yes. Can you speak a little? Can you give him the microphone? Because I am having a hard time hearing him. Thanks a lot, Alex.
So you just mentioned these Apache linking attacks and kind of indicated that they are not a big problem anymore, but like that is
well.
So this is a like there was recently the hack of the freedom hosting thing, which was exactly that vulnerability. And like I've looked at this quite a lot because I have a server configuration with an Apache, and there is no other solution apart from the GR security patch right now to solve that vulnerability. But we can discuss this maybe later. But
Okay, you actually have a point. I mean, that vulnerability can only be fixed at kernel level, and that was done by GR security.
yeah.
And it was a race condition on access to symlinks and comparing that the restrictions actually apply the way they should. But the way in which GRSec fixes the vulnerability is that it prevents the symlinks from being accessed if the owner doesn't match the source of the symlink. So I think, and I would like to be corrected there, that might be doable using SE Linux or any other mandatory access control if you define that processes with a specific with a specific role aren't allowed to access symlinks where the destination doesn't match the source. But I'm not sure if the semantics of the kernel are advanced enough to actually allow you to do that. Do you know, Hanno? No. Okay.
But I've researched this problem quite a lot, and what you're seeing is there seems to be a bunch of commercial fixes, but there's like nothing in mainstream Apache you can do. And this like kernel level thing from GR security, and I've actually been thinking now that GR security is no longer available to try to split out that feature and make it available as a separate.
If you do that, I can tell you that the spender is going to be really angry and he's going to try to do everything he can to stop you, but just don't say that I didn't warn you. I mean, I'm giving you support here, but yeah. Okay, let's talk also, there were also restrictions about the use of FIFO pipes, and they also had a really cool thing. I mean, they had a feature on which whenever, after you wrote to a specific entry on the proc file system, you would no longer be able to mount any new file systems in a read-write manner. That means that if you mark all your read-only file systems as read-only at some point during the boot, and then you call that function, they will not be able to be mounted again as a read-write, and therefore the attacker will have a harder time trying to modify the data that is found on those file systems. I'm also quite positive that such a feature can be implemented using a mandatory access control, but I don't think anybody feels brave enough to write a policy for that because it's going to be a pain in the ass, as a matter of fact, because most users will come afterwards like, yeah, you know, I touched this that was said to me on a random forum on the internet, and now I can no longer mount my USB pen drive and write my own presentations on it. Yeah. Okay, one of the really cool things that we had, and that could be really nice to see on the Gentoo kernel, I mean, raise your hands if you have used BSD before. Yes. So I guess that you guys know about jails and the difference between a jail and a chroot. Basically, a chroot means that you change the root folder for that specific process, whereas if you do a jail, you prevent the process from getting outside of the root that you have set up. On Linux, there is no such feature. I mean, we don't have jails. But GRSec actually modified the chroot call, so you can actually make a jail when using chroot. So it would be really nice to see proper jails implemented on Linux. Maybe, hopefully not using namespaces because, well, namespaces have been known to have some vulnerabilities in the past, so they are like not the most reliable feature nowadays. We also have things like enforcing process limits on execs, and that actually should be integrated into the Linux kernel. I mean, you guys know that if you do a fork bomb, then the fork bomb at some point is going to stop if you have a limit of the number of processes that a specific user can run. What happens if you actually make that when you cannot fork, you run some set2id binary, which is the limit of processes that will be applied. It will be the limit of processes will be the one of the users for which you have set2id the program. So for example, if you call su when you cannot do more forks, you will have an instance of su running there, and since the process will be owned by root, you will be able to do another fork afterwards that will then be able to call su again and keep doing that process iteratively, so you will be able to fill the memory even if there is a limit of processes, because you will have, say, 1024 processes owned by the user, and all the other processes will be owned by the root account. So what they did is that you were not able to run exec when you hit the limit of processes that you had, but well, I should say that that is not an totally effective measure, because if you make the fork bombs coordinate between themselves, so they will stay always at one process below the limit before doing the exec, then they will be able to actually carry the attack even if you enforce the process limits on execution. They also had restrictions to prevent you from accessing the MESC. I think that is now implemented into the Linux kernel. Not sure how secure that implementation is, but I think it is. And well, they had a mini mandatory access control thing called TP. If you want to read more about it, there is a really good document that I wrote a few years ago. On network side, they also modified the TCP stack so that you could never send a reply back if you didn't have a state for that packet. So basically that makes it a lot harder to run something like nmap, because you will not be able to get a reset or what's it called? A reset packet telling that the port is closed, or a INCP response saying that nobody's listening on that specific port. And that also prevents you from using an attack that is known as last ACK. The last ACK attack basically is that you prevent sending the ACK after you close the connection, so the connection looks as if it's closed, but it's not actually closed, because you have to keep sending the FIN packet on the TCP to the other side until you get a confirmation that it has actually acknowledged that the connection is closed. There were a few things like restrictions to the socket. That's a mandatory access control thing. A really cool thing that I think the kernel is working on is that they moved all the information about the process and the threads outside of the stack of the process. So that meant that you couldn't use a Stack Overflow attack in order to overwrite the user identifier of the process and become root. And they had a thing called active kernel exploit response. Basically, if GRSec detected some attempt at exploiting a vulnerability like a buffer overflow on the kernel, it would prevent the user from doing any further attempts. Basically, it would kill all processes of the user and prevent any new processes from the user being implemented. This could be done with a mandatory access control policy, but you will need to update the kernel in order to allow it to understand that kind of situation. And well, they had a shitload of kernel auditing information. I mean, you could log every single chroot, every single directory change, execution. You could log if there was any change to the system clock, so that your logs would not be skewed. And all that is something that we should really consider integrating back into Linux. And finally, and that's not GRSec related, we had shitloads of mandatory access controls. I mean, if you use Gentoo Hardened, you are going to have an easy time using Linux. Okay, easier time. I mean, it's still going to be painful, but a little bit less. We have quite good policies thanks to Swift and Perfinion. And they also provide really nice support on IRC. So if you guys want to test Linux and don't know where to start, consider using Gentoo Hardened. It might actually work for you. So I think we have like 15 minutes left. And so I'm going to skip the part where I talk about the GCC plugins, because it doesn't make much sense. I mean, the only interesting one that you will see is the constify one that marks data as constant actively. so that it can be put on the read-only memory and you can prevent an attacker from actually using it. So I'm going to make just a 10-minute introduction on how to install Gentoo Hardened if you have never tried to do that. There is a really nice manual called the Gentoo Handbook. Okay, have you used Gentoo before or tried to use Gentoo before? Yeah, I was looking at you because if you that were a Gentoo developer haven't used Gentoo before, you could be lying to me. Perfect. Okay, so those of you that have used Gentoo before know that there is a document called the Gentoo Handbook that explains step by step how do you install a Gentoo system on your computer. It's a lot easier than it seems. I mean, you just have to copy paste most of the commands blindly, and it will actually work. I know. It sounds stupid, but it actually works. I mean, it's amazing. So basically, there is two differences on the handbook that you need to apply if you want to make a Gentoo Hardened installation. You have to use a hardened stage 3 instead of the normal ones. If you try to download the stage 3, you will see that some of them are labeled as hardened. Pick one of them, the last one if you can. And you were supposed to use the hardened sources, but that is no longer possible because, this Saturday we are masking the hardened sources and we are removing them by the end of September because GCC is no longer providing new patches that we can use as the core of our hardened sources kernel. So if you want to use Gentoo Hardened, I can give you 3 different possibilities. You can use the normal Linux kernel. So you will then be using all these KSPP features and the scattered everywhere security features. You will find, for example, that the mesh restrictions are on debugging options. You can also use the Miniply sources. Miniply is a user, ex-user of GR security that is basically backporting all the 4.9 branch patches that are applied to the kernel to the last published GRSec patches, so you can use them, but you do so at your own risk because, as probably everybody knows here, when you are using a stable kernel branch, you don't get everything that matters backported. Only the patches that are marked as security, and not all security patches are actually marked for backporting into the kernel. So there is a risk that you will actually miss some patches that are on the latest, newest official version of Linux. Finally, strcat from Copperhead OS is working on a project called Linux Hardened that tries to pick up some of the features from GRSec and from the mainstream kernel and keep them in his own repository. And it works more or less well. I mean, if you ask me what should I use right here, right now, I will tell you that you should try Miniply patches because they are actually quite good for now. But you should consider moving to mainstream Linux on the future. And I think that covers everything that I had to say. I mean, do you guys have any questions or anything? Yes, please, Hanno, go ahead.
So with GR security probably not being available anymore soon, and position independent executables are going to be default with the next profile update in Gentoo. The question is what's remaining that Gentoo Hardened is doing, and I was considering writing a kind of provocative mail to the mailing list to say, hey, maybe we should just kind of kill Gentoo Hardened and say our goal is to just put all the things that Hardened once was into normal Gentoo.
The thing is that actually the Gentoo Hardened goal is used to be being some kind of playground where you could actually test all these really cool hardening features that will eventually be integrated into the mainstream Gentoo.
But for example, with PIE, I think the problem was that it was available in Hardened for more than 10 years, and it was basically applied to main Gentoo far too late. I mean, this should have been a default feature long ago. And so I'm kind of wondering if it shouldn't be more the goal to just make Gentoo itself or in general mainstream distributions itself more secure instead of having separate Hardened and having it as a kind of playground for future features. That's I think a good approach. But like right now, I don't see a whole lot left that's in hardened, and that's if we take GR security away, there's not a very big difference anymore between.
There is two differences.
Yeah.
We are using the strong stack protector instead of the default one. And we are using a stack check, and I'm not sure if a stack check has been enabled on Gentoo or not. I think it hasn't
so.
yet.
Yeah. The other thing was this linker thing with bind now. I'm not sure what the exact impact is, but
yeah.
But it's not a whole lot.
Yeah, and actually, well, since you have taken the microphone, I know that you were giving some really cool talks at FOSDEM about control flow integrity, CFI. That would actually make for a really amazing feature in Gentoo Hardened. So if you feel like integrating it, I would really support you on that. I think I told you at FOSDEM, but well, I want to make it now public so you get a little bit more of pressure. But jokes aside, if you want to get a CFI integrated into Gentoo Hardened, it's really a cool thing, and I would hope that we can get that working. It would be really cool if we could have CFI stage 3s, so people can use the stage 3 instead of having to recompile everything.
So I tried that, but it's you have to fix a lot of things for that to work.
Okay. Well, it's worth hoping anyways. Any other questions? Yes.
Yeah, so a short while ago I tried to, I was just in some informal discussions with some other Debian developers about setting Fstat check by default on Debian. And someone else linked me an email by someone on OSS security. He's actually, I think separately he is a GCC reviewer, but he was basically talking about how stack check gave him some problems. I don't understand all the details of what he's saying, but it seems like that it's sort of, rather than one big problem, it's a combination of several minor problems.
Yeah.
So do you think that it would be good for Debian or just other distributions or Gentoo main to enable this?
I think you should use a stack check specific everywhere, because at least on Gentoo Hardened, I have yet to see a bug that is opened saying stack check doesn't work. In the case of Debian, I strongly recommend that you start testing it first on the unstable branches. Yeah. And if it works there, then you bring back to the stable ones, as we do on Gentoo.
But you have used like major programs like Firefox, LibreOffice, like all of the big like stuff fine with Fstat check in your experience?
This computer here, it's actually using stack check. Okay. And it's a KDE5 system with Firefox, Thunderbird, LibreOffice, and all the other big programs. It works.
Cool, thanks.
So just so you know, it should work out of the box. I think the GCC developers are developing a patch to make a stack check a little bit better and more strong, because it's also a bit messy. They use 2 pages and they don't do so correctly. But as long as you have a kernel that ensures that the stack gap is at least 2 pages long, stack check does work. At least that's what I could infer from, well, spending a shitload of time documenting myself on this vulnerability.
And with these newer kernels, the stack gap is already above 2 pages, like they increased it.
Yeah, I think it's like 1 megabyte or something like that on the latest kernel, so like it should work without any problem.
These days it's like 256 pages, I think.
Yeah.
Cool, thanks.
Thanks a lot for your input. Is there any other questions or any other comments that you want to add? So, well, have a big round of applause, please, for Alex for coming up here and helping me explain how a buffer overflow works. And thanks a lot, everybody that has come here. It's been a pleasure talking to you.